Alright, having to make this video a second time, which is kind of annoying. So it probably won't be very good, and that's okay, because it's all good practice. And a little hard on the brain, though, physics. So we'll start. This is going to be about inertia, but inertia is a complex subject, got a lot to it. So it's a model of inertia, and I'll have to slide this up to get the last sentence in there. So anyway, so I'll play a Feynman clip and to get the ball rolling, so to speak. Just basically pointing out the current state of physics on the subject.
The motion to keep it going in a straight line has no known reason. The reason why things coast forever has never been found out. The law of inertia is no known origin. So
Alright, so so it's kind of an important part of physics, is recognizing the fact that that this is kind of a really it's more complicated than it might seem. So my drawings have some drawings on them already, which isn't too good. But the idea would be is that if you imagined an atom and you imagined the little bits inside of it, even the standard model, it has those bits in orbits. And the idea is you run out of a field, you run out of you can't use the same forces that apply to us on the nuclear level. It's they've already sort of used them up. But the idea would be is that you would have a nucleus with proton, neutrons in it, and then you'd have electrons out here moving about. And the idea would be is all those atoms have to move in a direction when you have velocity, and wouldn't it mess up their motion a tremendous amount? Like how do they know? How does the electron know that these bits are moving, and that it has to maintain its movement with that movement? And what's conveying that information? How does it know to do that? That's a very eccentric motion, and it doesn't have something like gravity to rely on as we know it. It has to rely on the forces connecting these objects, and which one is the possessor of the force, which one has the seed of the change, and how does it maintain that change. And so inertia is kind of important. You can't just use a momentum argument, but these little bits don't have momentum in the right directions. The argument's probably more I could argue it in a more complex fashion, but I'll try to keep it simpler. All right, so this does relate to gravity and all these other things, so I guess for the sake of clarity I will talk a little bit about the inverse square law and how that functions, why it functions, why force degrades over a period of time, especially with gravity, is that the force isn't communicated between the two objects. So you have to sort of think of, if you took a bowl, I should just use a bowl. If I had a bowl on this table, you could see that as a half of a circle, and the force of gravity, when two bodies start to interact with each other, the force is being irradiated from all the parallel surface of that sphere. And so most of the force will never get to the other body. Say if the other body was just a little ball here in space above the bowl, you could see that most of the force isn't going to affect it in a way. And that's sort of the inverse square law. That's basically saying the further you get from the bowl, the more that scatter is going to avoid the thing you're interacting with, and the weaker the force is going to be, the weaker the connection between those two things, because the force is being spread out over that sphere. Now if it was a wire, then it's only going to be part of that circumstance, and that's when it becomes r cubed. So the force weakens even quicker, because no, it's r cubed. Wait a minute, I was going to step on my own argument here. Is when the force is in all three dimensions, or both sides of the circle. Well, I'm not gonna make it more complicated for myself. I think it just means that it's in one of these quarters, but I just don't, yeah, somehow that spreads it thinner. Well, anyway, I don't want to mess myself up, but the point you could sort of see, if I flatten the bowl out, then the force all goes straight up, and no matter where you would go, you would have the same effect. So it doesn't matter how high you go above an infinite plane. If I smashed the bowl down flat and then I made it infinite in all directions, there's no way the force could ever evade me in terms of it being equal. Straight line force. Even though it's coming from an angle, it would still be straight line from my perspective. I would still be getting the equal amount of surface area force no matter how far away I went. So it's essentially like a laser beam, a perfect laser. Alright, so that's only relevant to the gravity element of it, but it's sort of an important reason why, well, it's gravity and magnetism, why this inverse square law. And the inverse square just basically represents the fact that the force is diluted because it's going in any element in the direction of the dimension. So this is supposed to be a representative of the three dimensions. So from how I'm looking at it, this blue line is the up and down, is the straight through the paper, and the other two would be the other two dimensions of left, right, forward, back, and this would be up, down. And you can see that from one dimension's perspective, the other two dimensions are always on the same plane. So these two dimensions are on the same plane, and this dimension is the one off the plane. And that's sort of important, but these are the only three dimensions in reality. There's no space dimension, there's no time dimension. This is all there is, and there's energy moving in these three dimensions. And so if I was to take what we're going to call a quanta, a bit of energy moving the speed of light, you could sort of like a photon, or what we call a photon is really two because it has a frequency, but let's just say the ton part of a photon. Let's just say an arrow, a quanta of energy, which it could be a graviton, a magneton, or a photon, and it's moving in one direction. If I were to tell you that, it seems kind of obvious. Yes, it has mass in the one dimension it's moving in, and it doesn't have any mass in these other two directions. There's no force moving in these other two directions. But if I was to take an electron, that's more like a sphere, and it has elements moving in all these directions. So it's constantly going back and forth, so to speak. So if this was to be a drawing of an electron, you could imagine a million of these little arrows, so to speak. There'd be one's all moving in the same direction, one's moving in this direction. But the point is they'd be constantly moving back and forth because the external pressure is constantly hitting them. And so as they're doing that, they'll be always moving a little this way, moving a little that way, always back and forth like the flip of a coin. They get hit a little bit more this way, then they go this way a little bit, then they get hit more this way, they go back the other way, but it would all neutralize out to basically a blob of water in space. It would find a neutrality over time and just be a round sphere. But clearly all active pieces inside of it. The pieces are still moving all the time. And so that's basically what matter is made out of, is these little force arrows contained in a pressure field, like a drop of water in space. And or in the space shuttle in a pressurized environment. If you put water in space, it probably will fall apart. I mean, purely empty space. But anyway, I don't want to complexify the argument. So you could sort of understand that if what matter is representing is a bunch of stuff moving in these three dimensions, and if I was to take just one of these pieces, that's moving the speed of light in one direction. And so you can't really bother it in any other direction. So that's why forces can't be affected. It's because they only have mass in the direction they're moving. So they can plow into something, but if they hit something, then they'll just create a reflection, and you really won't be able to tell that something happened. So we're sort of back to that argument. But if I bring an arrow in here to hit this arrow, what's going to happen is this arrow is just going to reverse, and this arrow is going to reverse, and you have the same world as you had before that interaction took place. You have one thing going this way and you have one thing going that way. So nothing really happened in a head-on collision. And that's sort of important to all this physics. It's an illusion of action, but there really isn't any change, and therefore there's no action. But something did happen, and that's the key to it. Something did actually happen. When two things collide, something's actually happening, but in effect, nothing happened. In the sense that by the physics, no rule was broken. And the only time that changes is if the thing that comes in is of a different polarization. So if a red hits a blue, then the red leaves this way and the blue goes back this way. We'll just use black for this example. And so something has changed. A black thing going this way is now a black thing going that way, and a red thing going this way is now a red thing going that way. So in that circumstance, the world changes. So when something of the same color hits, nothing changes. When something of a different color hits, something changes. And that's really the function of this whole thing. So, but anyway, what I would argue, the simple description of these three dimensions, it applies to motion in the sense that if I add blue arrows going in this direction, they will interact with the field energy ahead of them and they'll be reflected. But they use up the field energy as they hit it. So the more of them I send, they'll reflect from a further up position. So the more arrows that are going this way, the deeper into the field they'll end up going before they hit something to reflect off of, because this field is always staying the same. So if I send more in, I'm obviously going to go deeper into that field to reflect to go back. And the fact that I went deeper means I used up more time. And so the stuff that was going the other way has more time to hit something. And so in a sense this thing gets stretched, but it gets stretched in that direction. And that's essentially what velocity is. And as that's happening through the center here is where, this is what makes matter different than just field energy, is that what's going to happen is that the extra arrows going this way are going to essentially cause arrows going this way to be released. So if I put in extra blue going this, if I put something going extra in this dimension, what's going to happen is something in these other dimensions is going to be let loose, because this whole thing has to always stay the same size. And that size is dictated by the pressure of the field. So the pressure, that's why electrons are always the same size, is because they can't really be smaller or bigger, because they have to match themselves to the pressure of the field. So if there's more going one way, it'll release ones going in these other dimensions. And that perfectly matches the effect in, especially in electrons, of what's called EMF, or the electromagnetic radiation, or force, that's emitted by electrons moving in a conductor, or electrons actually moving anywhere, I mean being accelerated. So when it's gaining velocity, that is, arrows are being added, it will release arrows in this perpendicular dimension. So you can sort of see these two dimensions are perfectly perpendicular to the arrow of the major velocity. And these are essentially all gyroscopes, so they're always going to move to their main velocity, the velocity that is the addition of all the velocities that becomes, say, its heading, and these other perpendicular dimensions will be the perpendicular dimensions for which the energy will be released. So perpendicular, so if an electron moves this way, it releases its electrical or magnetic field energy perpendicular to it. And that explains this. And so you can also sort of understand that the faster I move an electron, the smaller these perpendicular lines get, and the less this back and forth going this way has to exchange directional information with these bits, the less it has to drag it along. So I've used the school of fish as an analogy, so maybe I'll do that again, because I think it works. The idea is that you're just basically, it's a conservation argument, kind of. If you have a school of fish, from what I just explained, you could sort of understand that if the school is staying in one place, well, that means let's say if I took a 5-second interval, the same number of fish have to go this way as down, as forward, as back, as left, right, or this, all these angles, the same number of fish have to be going both the opposite directions of each other. And so there has to be a perfect balance if the school stays in one place. Now if I add a couple of fish going this way, they're essentially going to have to, for this whole school to move, they're going to have to spread their speed or their direction against all the other fish. They're going to have to basically bump into every other fish and for one moment have it go this direction, and then it can go back to going its other direction. So I've used a dancer as an example. If somebody's dancing and I ask them to move to their right or move to their left while they're dancing, they won't be able to dance as fast. They'll have to take time away from dancing to do that. And so that's the time dilation element of velocity. But the real point is that it takes time for this stuff moving the speed of light to get from here to here theoretically, because it has to change all of this into moving one step, one quanta in the direction it's moving. So you could sort of argue that it doesn't have to, obviously the ones that are the percentage, the 1/4 of the fish, let's say they're going the right way, you don't have to change them, but you do have to change the ones going perpendicular, and obviously the ones going the wrong way would theoretically have to be changed. So you could argue that if this was the speed of light and this had 1,000,000 pieces in it, that it would take, say, 3/4 of it would be 3/4 of a million, 350,000 times slower than one of these. So it'd be 350,000 times the speed of light for each quanta that you add would have to be the amount of motion in this direction. So it'd be a tiny percentage. The school moves the speed of light. It would move just a tiny bit and be a very slow speed. And that's why you need a lot of energy or force to move material objects, because they have a lot of fish going the wrong way that have to be dragged along. Alright, so the real transition between acceleration and velocity is there's a complex mechanism that allows for that exchange. And again, that goes back to this argument that this stuff is constantly going back and forth through a center, and in this center this stuff keeps banging into this other stuff, and it forces the green to go this way, and then the blue ends up going that way, and then they end up hitting something else, and then it gets changed back to the blue, and but it adds up in the end that you still have more arrows going this way than you do this way or this way or this way or any of the other directions. So in the end you're still going to be hitting the forward field with more arrows going forward, and that will be maintained as a velocity. So once you add more blue, it becomes a permanent addition. Even though it's going back and forth, the point sort of is that it goes forward deeper and then it goes back less far, and it goes forward deeper and it goes back less far, and that's essentially what a velocity is. So a velocity is essentially a kind of, you go forward and then you go back, and then you go forward and then you go back, and then you go forward and you go back, go forward and you go back. But that's what's happening internally. But the end result is that there's a net motion, a velocity in this direction, and it's going to be a percentage of what the force that went in will be distributed over the mass, and then the mass will move that percentage, whatever the ratio is of fish you added to the number of total fish. The ratio will decide how much velocity the object actually acquires. Yeah, good enough explanation, I think. So inertia really is, you could have an inertial state that's, say, technically where you were in perfect balance, like all the lines were the same length and the electron was in a perfect steady state. But most circumstances you're going to realize that in most places in the universe there's going to be some point where you were accelerated and you still possess the velocity that was the product of that acceleration. And things in the solar systems and in the galaxies and in the universe, we have a lot of compound motion, so at every one moment our velocity, when you add up all the directions we're moving, they all have to be added up, and you get a little bit this way, you got a little bit that way, you got a little bit going back with this way, you got a little bit that way. You add them all up and there'll be a vector, and that is your true velocity in a direction. And the point would be is that velocity is likely to be a lot slower than the speed of light for material objects. And I would argue that the faster objects start moving, the more they release these extra dimensions. So if I were to talk about an electron, I could say an electron not moving would kind of be round, sphere, but one that's moving in a direction is going to start getting, it's misshapen in the sense that there's going to be more motion in one direction than in these perpendicular directions, because you're losing these arrows. So in a sense, the matter will change its shape as it changes the proportion of arrows going one way versus arrows going the other way. But these are tremendous velocities that you would be talking about to be able to have a substantial shape change. We don't even have any examples of matter even going, say, 10% of the speed of light, let alone 50%, which you would need to have this kind of a shape. So a 10% change wouldn't be that far off of a circle. It would be a little bit of a fat circle. And that would be a very fast speed. It's 3 million meters per second. It would be it would be fast. 150,000 miles a minute or something. I don't know. Really fast. A lot faster than we've seen anything move. And I would argue that the matter at those speeds would start to deteriorate. It would just start to fall apart, because everything in the atom is tied to very strict kind of rules about their distances from each other and their charges. And those charge distances would start to change, which means that the positions would start to get eccentric and change, and there's some point where that would cause a lot of degrade in the shape of the atom. But an important feature would be is that as that does happen, it would also decay. It would cause the elements that are decaying to likely decay slower, because more time is being spent going back and forth in one direction than in the other directions. And decay is probably dependent on, say, back and forth 100 times in this direction, and as you're losing these other dimensions, it takes longer for you to do those 100 times, and that would mean the decay rate would slow down. So the functions of the atom would start to slow down as the atom is spending more time doing one thing, which is going in a direction. So it's sort of back to the dancing argument. I guess I've made this point before, and I don't know how directly it's related to inertia, but it's directly related to the complexity of calculating velocities. But the thing with time dilation and, say, GPS satellites is sort of interesting. We're standing in very heavy gravity here on Earth. The satellites are in light gravity here further out, well, lighter gravity. The trick is that people originally thought that the satellites were going much faster than us, 20,000 miles an hour, and we don't move nearly that fast on the surface of the Earth. But the trick is that we're in the heavy gravity, and as I'm pointing out, the field energy is coming down, hitting us, and we're still accelerating. All the nuclear bits are still moving inside of us down. They're getting accelerated down, and then the Earth ends up pushing them back up. So in a sense, we're constantly bouncing on the surface of the Earth. So in a 5-minute or 5-second period, we'll bounce, 40 times, let's say. But a satellite in less gravity, it might only bounce 10 times. So we're bouncing 40 times, it's bouncing only 10 times, and you can kind of understand that if I put less bounces in here, that this distance is going to be a lot longer than this distance. And therefore, if we're going to get to the end point at the same time, this guy's got to go a lot faster. So in a sense, our velocity is much higher than the satellite going 20,000 miles a second, because we're bouncing on the surface of the Earth and therefore traveling more distance, technically. And so that's why we have to have our clocks adjusted, making them go faster, because we're the ones going slower. We're in the live longer position than the satellite is. The satellite's getting older faster than we are, even though it seems to be going faster than us. We're in the heavy gravity, and we're actually going faster and aging slower than the satellite. Yeah. I have a cigarette I have to get rid of. Thank you, person who's yeah, very nice. I just smoked the last of my Christmas cigarettes, so it's nice to have. I call them New Year's cigarettes. Thank you. Hopefully I can make them last that long. All right, so let's see. Do I have to add anything? So yeah, this isn't done as very well because, like I said, it's the second time I'm doing it, and I'm a bit fatigued. But I just wanted to get it done, and then I can do it again, do it better in the future. But the idea is that inertia is a real thing. It's a real state you have, and it's an absolute state. You're moving through the universe in an absolute vector at an absolute velocity, and all of the bits inside of you are all stretched in the direction of that velocity. And if that velocity is increased enough, you're going to lose your material structure, and you'll just end up becoming a bunch of arrows moving in one direction, the speed of light. So in a sense, if you fell into a black hole, the argument is you're going to go with the speed of light very quickly. Well, as soon as you do, you're no longer matter. You're degraded. You've converted your matter, because matter is these three dimensions. Once you're not in the three dimensions anymore, you're not matter anymore. You're just one-dimensional energy. So force always moves in one dimension, and matter is conformed out of force locked in all three dimensions. That's the definition of matter, or at least two of the dimensions. Can't say for sure. Some of these elements inside of a atom might just be two-dimensional objects. They might only exist in the two dimensions. Have elements in two dimensions, and not have the third dimensional piece. But can't say for sure. I think there'd be a problem. Well, probably not. It just seems to me. Yeah, no, I won't make any arguments because I haven't thought enough about that. But I was just thinking that you'd still be losing that center piece, and that center piece seems to be very important to the exchange of how you make force meaningful. It really happens in the center. That's why everything's really coming out of a center of gravity. Those centers are the vital place inside of all atoms or material objects, and that's where all the action is, so to speak. Alright, so I think this is enough on the idea of it. So acceleration is really the collection of a polarization. I guess that would be an important thing to say, is that there's two kinds of energy in the universe. There's black, and where's my red pen, let's say, and we'll say red. And that's really plus and minus. So electrons are made of all, let's say, the red, and protons would be made out of all black. And the interactions are constructive in the sense that these elements, the red elements, always reflect off of the black elements. They can't be absorbed, and vice versa. And so these objects end up being attracted to each other, where two black objects would end up being repelled because all the red would be reflected back and forth between them. So the closer they got to each other, all the reds would start bouncing back and forth faster and faster and faster between them, and create more and more pressure pushing them apart. And I don't want to get into, I mean, that's a video for another time. I mean, it's important to velocity just to understand that the force is this, and if you're the same polarization of the force that hits you, like an electron, then it'll absorb that fish will move the thing forward, and if nothing else stops it, it'll maintain that acceleration. The acceleration will become its velocity. And if it's not the same color, then it can't absorb it, but it will reflect off of it. Okay, so if a red hits the black coming this way, the black will reflect and the red will get stuck between the two blacks, as I was pointing out. Yeah, but like I said, I don't want to get into that argument. But it's really just the fact that you can absorb or you can have a reflection, and that's how force affects other things. So it either gives it acceleration in a direct sense by absorbing and replacing some element of what it possesses, or it's just a reflection that maintains the form or shape of the material body. So it's the pressure field. So the red arrows are the pressure field for the black arrows. The black arrows are the pressure field for the red arrows. And if you figured the whole universe started off with an even number of black and red, you know, the same number, it might be argued that if there was a difference in the size of, say, electrons and protons, the difference would sort of be reflected proportionally, in the sense that you could realize this difference in the sense that the small number of red arrows left over are the pressure on the electron, and the number of black arrows left over are the pressure on the proton. Now yeah, so but you wouldn't use so the the complexity of that is that it could be exactly the opposite of what people think, in the sense that we can only measure these things based on how much energy they seem to possess, in terms of what we can measure as mass, and you can only measure that based on how they affect each other. And so we don't really have a good measurement. But the truth is the electron might be in actual fact bigger than the proton, but the proton's under more pressure, so what's inside of it could be more energetic, in the sense that the field energy that it's going to affect is greater. So there's more potential field energy, there's more black free arrows for it to be affected by than there are red arrows for the electron to affect. But that gets into a complex conversation about how you can measure almost anything this small in a universe where we can't really see any of these pieces, because the only way to see them is to bounce force off them, and force will distort them so much that you can't really see it. It's like if photons were as big as, say, basketballs, you couldn't throw them at a bird to see how big it was. Probably not a great example. But anyway, that's probably enough. So anyway, till the next video in this series, and such, and so forth and whatnot.